Welcome to chapter 8. Here's a second question. We're given a sorted array and we are asked to count the number of comparisons required to find the target. We can write a program to accomplish this. So we start by initializing the counter to 0 and then increment it by 1 every time we iterate through the data. If the target that we're looking for is the element in the data, then we mark that the target is found. If it is greater than that, there's still no need to continue searching. We can just get out of the loop since the data is supposed to be in sorted order. So that's about it. So we require 5 comparisons for locating 9 and it's found in the data. We required 7 comparisons for locating 11 and the target was not found. Here's the third question. We're not told that the array is sorted. So all we have to do is a sequential search. We have to walk through the entire array to locate an item. If it is found, we return true. If not, we return false. In the textbook, they just given fill in the blanks, but here's the completed program. So 9 is found, 14 is also found, 25 as well, but 0 is not found. Let's now turn our attention to the fourth question. We're asked to write a function to insert an element in a sorted list only if it doesn't already exist in the list. So we're going to make use of the bisect module. Remember that the bisect function works only for data that is in increasing order. So let's consider a sample list here, D. It has elements 0, 20, 20 and 21. The bisect method returns the position to the right of where the insertion is supposed to happen. So for example, if you want to insert 0, it's going to return this position. If you want to insert -1, it is going to return 0 because this is where the insertion should happen. If you want to insert 20, it's going to say that you want to insert it here just before 21. And if you want to insert 21, it's going to point you to the last position. This will become even more clear if you go through this example. If A is an empty list, so it has nothing, and if you bisect, if you want to insert 21, then it's going to point you to the right, saying that you want to insert it at position 0. Having seen this information, let us now move to this particular problem. First, if the array is empty, then you want to call the append method to add data. If not, locate the position where you want to insert. If the data in the previous position is also the same as the data that you want to insert, so that is array of position -1 contains the same data, then don't insert. If not, make use of the list insert API and set the data. That's about it. So here's the run. It doesn't matter whether we add data in increasing or decreasing order, the output is still the same. You can go through the main function. Here's the run that matters the most. If you add data in random order and if they contain duplicates, we still get a sorted list with just the unique elements. The fifth question is straightforward once you understand the fourth. Here we are asked to insert the data into an array only if it's going to be a duplicate, and we still want to maintain the sorted order. So if we consider this main method, we have 1, 2, 3 in the list, and when we try to add elements 1 all the way up to but not including 4, then only 1, 2 and 3 will get added, 4 won't be added. Even if we make it say 5, the result won't change. Let's see how this happens. So when we bisect and we get a position 0, it means one of two things. Either the array is empty or the data that you're trying to insert is smaller than the very first element in the array. And this means that it's obviously not a unique data point. So we don't want to insert. At the same time, we still want to compare against the position -1 location to see if it's the same as the data that we want to insert. If so, then we go ahead and insert the data. That's about it as far as the fifth question is concerned. Question 6. takes us in the reverse direction of the previous questions. Instead of inserting, now we are going to delete from a sorted list. The same idea holds. So we try to locate the position using the bisect method. If the position is non-zero, that is if the array is basically non-empty, and if we can check that the location that we want to delete, as in array of position -1 equal to the data, then we can use the del built-in to remove that particular location. If not, we inform that data was not found. So A here contains 10 elements, 0 through 9. When we try to remove elements in inserting order or in decreasing order, it doesn't matter. All the elements get removed. Even if we try to remove in random order, we can remove all items. Finally, as a negative test, we try to remove missing items, and the report comes back that these elements were not found in the array. On to question 7. We're asked to remove from a sorted array only if the data is already a duplicate in the array. So let's consider D here. Out of this entire list, we can remove only 20 because 20 already has a duplicate. The rest of them cannot be removed. A gentle reminder, when you try to bisect D, that is, you search for the insertion location for an element 20, it's going to return this particular location. That is, it's going to be towards the right of all the duplicates. So that's why we check for position -2. We want to ensure that position -2 is greater than or equal to 0, and the data is the same across these two positions, position -1 and position -2. Then we can go ahead and delete an entry. If not, report that duplicate not found. Here's the run. So we can remove items either in increasing order or decreasing order and random order. We should get expected results. So if we look at, I'll just look at one code block with you. You can do the rest yourself. So we should be able to remove 1, a single 4, and that's about it. So 2, 3 and 5 were not found. We got rid of a single 1. And we have 2, 3, and instead of 4 4s, we have 3 4s and then a 5. We couldn't remove 5 and 1 because they didn't have duplicates. That's about it as far as the 7th question is concerned. Here is a variation of the 7th question that's likely to pop in the exam. Given a sorted array, remove all duplicates. So if this is the input, then upon running the program, this should be the output. Here's a snippet that gets it done. Let's go through it. So initially, have a handle to the current variable, keep a copy of it, and keep iterating in a while loop. Remember to use len of a. This is important because when you try to remove an element from a list, the size decreases, and you want to compare that against your index. Don't use a for each kind of syntax wherein you say for element in array. That's not going to work. So if a of I is current, then you pop. If not, then current becomes your element that you're visiting, and you increment the index. That's about it. Let's look at the 9th question. We're given the runs conceded in every over as a multidimensional array. Each inner array corresponds to the runs conceded per ball. We're asked the following: find the most expensive over, find the overs where least number of runs were conceded, and the total runs scored in the match. Let's now solve each of those. They've asked us to find the most expensive over, so it is sufficient to report just one of those overs where the score is the maximum. So if there are 2 overs where the runs conceded is 10, then it is sufficient to report just one of those overs. So that's why we're going to return just a scalar value. So we iterate over the overs array, and for each inner array, that is for each over, we find the runs conceded, find the maximum of that, and maintain the index. Finally, we return max index plus 1 because the index is 1 less than the number of over. You can't say 0th over, we'll say first over. That's about it. And for this particular problem, over number 1, which corresponds to this one, is the most expensive over. The second part, they've asked us to find the overs where least number of runs were conceded. Since they're using plural, means that we can have multiple overs where, say, no runs were conceded and we have to return all those overs. That's why we're going to maintain a list. Again, if we have never seen a minimum run per over statistic, or if it is greater than the runs this over, then we reset these two variables. If not, if the runs is equal to the minimum runs per over, then we append. And finally, we return the min overs variable. Turns out that this is the one. All zeros is the least one. Let's just change this to 0 and see the output. So there we go. We have 4 and 5. That's about it for the second part. As far as the third part is concerned, they're asking us to find the sum of all the entries here. It's straightforward, right? Just iterate through the overs and keep adding the sum to the running total and return the final sum. That's about it.